Welcome everyone to the HPWH Hydronic Heat Working Group. This is our third meeting of the year. Have to read the compliance statement because we have multiple manufacturers on here. So HPWH is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other HPWH meetings, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product or accessory. Here's our agenda for today. Welcome. I'm welcoming you now. And then we're going to have a presentation from Pierre at Harvest Thermal on heat pump heating and hot water with thermal energy storage. We're leaving plenty of time for questions at the end. And then I have a few housekeeping and other closing items to chat through with everyone and some requests if folks can provide me with either raised hands or documentation. For those of you that are new, feel free to raise a hand or come off mute. Otherwise, or even if you are new, feel free to drop in the chat your name, pronouns, organization, and title. Give it a second to see if anybody wants to say hi.
John Heller here. I haven't joined this group before, but it's a really interesting follow-on to the work that I've been doing with the commercial heat pump water heaters. Moving to air-to-water heat pumps for space conditioning is an obvious next step for technology development. So interested to be here.
Thanks. Welcome.
Good afternoon, everyone. My name is Phil Bickle. I'm a program manager at Efficiency Vermont, and I manage our HVAC programs, which includes all of our heat pump programs, and which is including an air-to-water heat pump rebate. So nice to be here. Thank you.
Welcome, Phil. Okay. So you can read the purpose here, as I was mentioning to Charles as the meeting was starting. This is really to fill a need in terms of being able to get experts together to talk about salient issues of the day with regard to air-to-water heat pumps. There are similar working groups for air source heat pumps, or your ductless and unitary systems in there, and hot water systems like unitary heat pump water heaters. This is for air-to-water heat pumps that potentially can serve hydronic heating as well as cooling, combi setups, and thermal storage. So without further ado, because I didn't leave much time, we're already late. I will pass it over to Pierre. Pierre, is it all right if I make you a presenter?
Of course.
And you control your own presentation?
Yes, thank you.
All right, that is, I think the settings have you automatically as a presenter. So if you go ahead and share, it should work.
As this.
Yep, perfect.
Okay. Well, good morning, everybody. Shall I just get going?
Yeah, that sounds good to me.
Okay,
thank you for
great.
being here, and looking forward to the presentation.
Well, thank you for having me. I think you set expectation by saying we would have the top experts on air-to-water heat pump and hydronic heating in the country on this call. So it's an honor to be here. Thank you for taking the time. I see some names I know from my previous role at NRDC, and for those who haven't had a pleasure to meet, I was at NRDC for 12 years prior to co-founding Harvest Thermal, and I now lead product and operations at Harvest, and I'm excited to give you a little bit of a overview and have a discussion about what we do and how we fit in the hydronic and air-to-water heat pump space. So in a nutshell, we provide a thermal energy storage solution for heat pump space conditioning and hot water. And the problem that we set out to solve is the issue with scaling heat pump. Heat pumps are wonderful devices, super efficient, but they also face some challenges in scaling, primarily the fact that the economics are not necessarily always favorable compared to gas. They're good compared to electric resistance for sure, for propane, fuel oil, but it's challenging to break even. Sometimes costs are even a little higher than gas, depending on local gas and electric rates. And it's going to be difficult to scale if we don't provide compelling consumer economics for mass adoption. The other challenge that we have is that they tend to, heat pumps tend to operate at times when the grid is there's high demand on the grid, and it's not necessarily the cheapest and cleanest times to operate the grid. So in terms of market, we see the need for both more cost-effective solutions for customers, both consumers and multifamily property owners in the residential sector, as well as from utilities and grid operators to find more grid-friendly solutions that can help scale without increasing grid costs. So what we are doing is a combi system, or integrated, whatever the terminology is, with a twist. It's a little different from what many combination systems are on the market. We do provide domestic hot water, space heating, space cooling, and thermal energy storage, and that's a key differentiator. That we provide thermal energy storage in order to enable load shifting of both domestic hot water, but also of the space heating load, to shift it off peak and help reduce both customer and grid costs. The other twist is that we don't really use an air-to-water heat pump. We use a heat pump water heater, a CO2 heat pump water heater, the Sanco 2, which I'm sure many of you are familiar with. And the reason we use it to generate hot water for both hydronic heat and hot water, storing it in a tank for thermal energy storage. And the harvest pod is where the magic happens. It's both a hydronic controller and an electronic controller. So from a hydronic perspective, think of a hydronic system, often installed, in the basement. You're going to have on a wall somewhere. You're going to have pipes and pumps and valves and sensors, and it's pretty expensive to install because of all the site installation needs. So what we did is we integrated this in a box at the factory, tested at the factory, and plug and play on site to reduce installation costs and make it cost effective to install. So this is the basic of the hydronic system. On the heat delivery side, we support a range of distributors, of emitters, if you want. The primary one, we do mostly forced air. That's the majority of our market, with a hydronic coil in a variety of air handlers. We also support radiant distribution and low temperature emitters like wall panels, fan-assisted wall panel, hydronic baseboards, hydronic mini splits. But just to be clear, I think the majority of our installations so far have been forced air with hydronic fan coils. And so far, we've only talked about the heating side, and we provide cooling as well, and a little different. So for cooling, because the Sanco 2 only provides heat, so heat pump water heater, not an air-to-water heat pump, we need to integrate with a separate air conditioner or heat pump, which is a regular air-to-air heat pump for cooling and for supplemental heat. So we can also use the heating cycle of the heat pump, if it's a heat pump, to provide supplemental heat and augment the capacity of the Sanco 2 heat pump to go up to 4 tons of heating capacity, where the hydronic system will always provide the first 2 tons, and then anything above that will be provided by the supplemental heat pump. So a little more about the controller. I mentioned it's a hydronic controller, but most importantly, it's a smart controller, and that's what makes the system work. The electronics and those cloud-connected electronics controller in the pod is what turns a regular water heating tank, humble 100-year-old technology, into a smart thermal battery by modeling its stratification profile, and we have 2-gallon layers, and we know the temperature of every layer at any point in time, and we recalibrate it constantly by measuring inputs and outputs. And that knowledge of the state of charge is the basis for all the load shifting, the charging, the discharging, the entire algorithm. The pod also learns how occupants use heating and hot water over time and how it correlates with weather and with other factors, and uses that to forecast the heat and hot water needs over the next 24 hours. So then you have the state of charge, you have the demand forecast, you have a price forecast from either from a time of use or from the utility. And you can use that to optimize when to run the heat pump, when to charge thermal storage, to be able to serve occupants' needs at the cheapest and cleanest times of day. So running this decoupling when to run the heat pump and when to deliver that heat and hot water, so that in order to optimize for energy costs. The pod also controls delivery, and that's really important because in order to achieve a high storage capacity in the system, we use a low return temperature. So we have a high temperature delta across the delivery system, typically around 70 degrees Fahrenheit, which means that with 120 gallon of hot water and 70-degree delta T, we are able to achieve about up to 75,000 BTUs of storage. And I have a slide to talk a little more about this later, but that's really a key differentiator, because that's necessary to be able to shift not just domestic hot water, but also space heating loads. So key differences with conventional air-to-water heat pumps. The first one is operating temperatures. By using a Sanco 2 heat pump, which is very good at heating water in a single pass to about 150 degrees, we are able to operate it at a high temperature without a significant efficiency penalty. And the proof is here on the annual operating efficiency that we get. We get about 3.8 average annual operating efficiency for the Sanco 2. And as a system perspective, including fan and circulator pumps and thermal losses and controls and everything, we're around a 3.0 COP average annual, which is on par with the best variable capacity heat pumps, and that's before arbitraging for price. So it's both high efficiency and beyond that, low energy costs. From an installation perspective, we don't use a buffer tank. We don't need a circulator pump added, because there's one in the Sanco 2, factory installed in the Sanco 2, and we've got one for the heating loop in the pod. So it's again no additional circulator pump to install, and the thermostatic mixing valve is also in the pod, making it again easier to install. It is an open loop design, meaning that we don't need a heat exchanger on the distribution side, except if you do radiant or other non-portable distributors. But for forced air, we have a NSF 61 rated coil, and we have circulation controls to make sure the water never stagnates in the distribution system, and that avoids the need for heat exchanger, which increases efficiency. Storage capacity, I alluded to that earlier, and that's a key differentiator. We achieve, on the electric side, we achieve between 5 and 7 kWh of storage capacity, and we cycle the tank twice a day. So if you want, in effect, we're shifting between 10 and 14 kWh of heat every day in the winter, twice a day in the winter, once a day in summer. And that's a lot higher than you will see with typical combis. So, there's a number of other combination systems in the market, once name manufacturers, but typically they are air-to-water heat pump with an indirect storage tank for domestic hot water, lower storage volume and lower temperature typically. And those systems typically only have a 1 to 2 kWh of storage capacity. That's not enough to shift space heating load. It's enough for water heating, but not for space heating. Even PCM, phase change material products on the market today have a storage capacity around 3 for the biggest models, residential models about 3 kWh. Again, not enough to shift significant space heating loads. So the key differentiator in the design, we designed the system to be able to have enough storage capacity to make a meaningful difference in terms of space heating load shifting. And I've mentioned that a little bit, but that's by using single pass charge and discharge of the system, and 120-gallon tank. We can do 83-gallon as well, mostly for multifamily, which is space constrained and lower heating loads. But the majority of our customers opt for a single 120-gallon tank, some with 280-gallon tanks, so 160-gallon, and you get more load shifting. There's a little bit of a higher cost to that, but that's also a quite popular configuration. So why thermal energy storage, and why do we need, what is the big thing about load shifting? So imagine you're a grid operator for a day. So here's your day from midnight to midnight. Your job is to balance the grid and keep the lights on. And you have heat pumps operating when it's cold, when people need heat. So it's primarily in the morning, when you don't have, in the winter morning, sun hasn't risen yet, so before sunrise, and then in the evening after sunset, there's no solar energy on the grid. Maybe a little bit of wind, but there's also high demand and limited renewables, and you need to supply power for heat pumps, and that's increases. The more heat pumps you deploy, the more you increase your demand at a time when you don't have high renewables on the grid. So the solution with thermal energy storage is to run the heat pump in the middle of the day when you have abundant solar and lower demand in the winter, and using that thermal energy storage to store that energy and be able to use it later in the day, particularly in the evening. You can see that green curve goes nearly flat in the evening. And that's because we are able to discharge thermal energy storage to meet heating hot water needs for the entire evening. So it depends on the home, depends on how big the load is. But for many homes, it's all, and for most homes, it's a significant share of evening load shifting. And then depending on the season and the morning load, you may need to top up or recharge thermal energy storage in the morning at night so that you can meet heating loads in the morning. And then the primary time for charging storage is in the middle of the day. I mean, it depends on local time of use rates and local grid conditions, but most increasingly grids are shifting to have low cost and the cleanest electricity in the middle of the day during the peak solar window. So this has two benefits: price arbitrage for those of you who are on time of use rates. And I know it's not everybody, but it's more and more people as renewables are getting more common, and also as the smart meter rollout is nearly complete with over 80 to near 90% penetration of smart meters today. So we're seeing an increase in people who will be able to benefit or can at least opt in, if not opt out from time of use rates, and be able to benefit from price arbitrage by using thermal energy storage. The second is temperature arbitrage, right? By running the heat pump in the middle of the day when it's the warmest time of day, instead of running it in the morning when it's coldest time of day, or in the evening, which is also cold, you can gain about a point of COP. And that's a significant, efficiency gain compared to a heat pump that will run instantaneously with demand. Charles, you have a hand up. Do you have a clarifying question before we get to Q&As?
Let's see. Well, I was on another presentation given out of Arizona just recently, where they took a completely different approach to operation time, because midday electric consumption there was the highest demand. Yep. So they were using storage to, nighttime when there's low demand, they were storing up the water temperature, so they didn't have to run it in the middle of the day. So this is a completely opposite perspective, it seems.
Yeah, thank you for the comment. And every grid is going to have its own local conditions, and this is the harvest pod is adaptable. It basically takes a price stream as an input and will optimize for whatever price shape you give it. So whether it's middle of the day, middle of the night, whatever is the cheapest time for the local grid or even the local distribution circuit is something that the pod will optimize for.
Oh, that's a great idea. Thank you.
I have, I think, another couple slides that show that in more detail. Before then, let me move forward just to make sure we have time for Q&As here. So what markets are we deploying to? Our primary market today is single-family retrofits. It's about 90% of our projects. We started earlier this year, last quarter, we started with multifamily. We did our first deployment last quarter. We're in the middle of doing our second one. And these are, kind of garden-style apartments with in-unit HVAC and domestic hot water. It doesn't have to be garden style. We can do high-rise or other types of apartment, but it's basically units that have in-house or in-unit heating hot water, either a gas combi, a combination system fed by a gas water heater, or it can be a furnace and a typical gas or electric water heater. And we can retrofit this with a harvest system. That's all we're doing in 2 projects right now. And we also done some deployments in new construction, both in custom new homes, architect homes. We're doing quite a few of those, but the sales cycle is quite a longer because these homes take 6 to 12 months or more to design and build. And we've done a pilot with KB Home as well in a production home and looking at how to scale that over time. And in terms of geographic coverage, we started in California, still our primary market today, but we've been expanding beyond California up and down the west, up the West Coast and Oregon, Washington, and all the way up to Alberta, Canada. We have 2 systems working in Edmonton. So for cold climate proof points, that's a good one. With design temperature, I think probably in the minus 30 or 40. And we have systems in Colorado and New Mexico as well. And we're currently working with our friends at Efficiency Vermont to plan a pilot in Vermont and several pilots, hopefully, moving forward. And we also were talking to other utilities in the Northeast and a couple other places. But we want to be strategic and targeted in how we expand, and want to make sure that we have, as a small team, we want to make sure we do it right and at the right time. So looking at opportunities from both utility interest and support, market conditions, customer interest on how to expand. So in terms of results, as of last month, we were up to nearly 350 systems sold, and the results in the field speak for themselves. We have, so the little chart on the right is every dot is a average COP over 1 month for one system. And it's really right around 3.0, more or less, depending on how much heat and hot water people use and relative impact of thermal losses. Thermal losses, just to give you a sense, on average are around 5%. So it's actually better than you get from a electrochemical battery. The round trip efficiency, electrochemical battery, maybe Tesla advertises 92% efficiency. When new and then it degrades over time, we get about 95% efficiency with no degradation over time, right? So and you do that only if you control it in a way that you minimize how much you charge it and how long the hot water resides in the tank, right? Because the longer it stays in the tank, the more heat is going to lose. So the algorithm is designed to optimize efficiency by minimizing, thermal losses. In summer, for example, we only charge maybe 30% of the tank. We just charge enough for domestic hot water use. Because it's completely stratified, we can just basically charge the top third of the tank or the top quarter of the tank or whatever is needed for this particular home to meet their hot water needs, and then a margin, right? So that minimizes thermal losses over time, and it allows us to have this level of high efficiency and low thermal losses. So this, again, as I said, this level of performance is comparable with field efficiency of the best variable capacity heat pumps, and that's before price arbitrage. So with price arbitrage, we can beat those heat pumps and provide a more compelling value proposition to homeowners. In terms of load shifting in action, so this is a time of use schedule. It happens to be PG&E with a 9-hour high or mid price window from 3 p.m. to midnight. And in green, you have the times when the heat pump was operating in the winter. So you can see a dual peak, middle of the day, middle of the night to recharge for the morning. That's only for the winter. In mid seasons and shoulder seasons and summer, you'd only see the peak in the middle of the day. And the system was able to shift 90% of the load off peak. And importantly, without the need for people to curtail their heating temperature to preheat or pre-cool, or it's basically no compromise of customer comfort. They get everything they want from the thermostat, just thermal battery is doing the work in the background with no compromise for customer comfort. And this chart is an average on an entire quarter. So it's an average load check, basically, right? So it's not just one particular day when it was working really well. It's the average over time. You can see that there is a little bit of usage, especially towards the late, the end of the period. And that's because on some days, people do use more heat or hot water than the storage capacity of the system. And as a result, the heat pump will kick in. The priority is always to provide heat and hot water that people need, so they never run out. And even if it means running on peak when necessary. But we're trying to minimize that as much as possible. And we can also do dynamic prices. And so that's not quite common yet. We're seeing pilots, particularly one in California, the CalFlex Hub pilot funded by the California Energy Commission and run by Berkeley National Lab, where they send us a hourly price signal. So we got the next 24 hours worth of prices every hour. And we basically had to try and optimize the heat pump operation for that price signal. So prices here are in the blue bars. And red, you have thermal demand. In green, you have electricity used by the whole system. And you can see that most of the electricity use was in that valley where you have very low prices. And we're still a little bit on peak. But first, you have fan energy use and circulated pump energy use can't be shifted. So that remains. And then sometimes we do need to run the heat pump at, outside of these solar hour windows because there's just not enough hours in the middle of the winter during the solar window, but it's minimal. And by doing this, I mean, this is a kind of fictitious price signal. It's not a real one, but on that price signal, we were able to reduce operating costs by 50%. So it just points to the potential as those prices become more available over time to provide really compelling value to the homeowner for participating in demand flexible programs. What about first cost, right? That's probably the biggest factor in terms of mass market adoption. What does it cost to install a system? I mean, to be honest, it does cost a little more because we have thermal energy storage and everything goes with it. It does cost a little more than the comparison, the baseline, which is a regular heat pump, HVAC heat pump and heat pump water heater. But with incentives and tax credits, we are able to be cost competitive and sometimes even depending on the local incentives, lower cost upfront than the HVAC heat pump and heat pump water heater baseline. Those particular prices are in the Bay Area, which is not, we had just happened to have with the tech program a lot of data points, about 30,000 data points in California. So that's a really good data source. We don't have as many data points elsewhere, but Bay Area is one of the highest price markets in the country. We expect that prices will be lower in many other markets. This is already relatively affordable for swapping out both heating and hot water. In multifamily, we have so far seen sub 10K prices. Again, depends on local incentives, but it's economies of scale, smaller configuration systems allow us to get into the single digits, and sometimes with a good stack of incentive close to zero. Total cost of ownership is typically about up to 10K, and that lower than with regular heat pump systems. So that's including upfront costs and operating costs of the life of the system. The real comparison baseline should really be a HVAC heat pump water heater, and a lithium-ion battery, and with significantly cheaper than that, even after tax credit and incentives on the battery side. Still, I think that's good. It's a good start. We're only in the hundreds of units, so very low volume today, and our job is to scale, reduce cost, to make this even more compelling, be less dependent on incentive, and eventually no longer dependent on incentives, and be able to scale in the market. John mentioned that we need to talk about freeze protection. I know there's a lot of but some of you, I'm sure, live in colder climates where it's maybe a concern to have a Senko 2, which is a portable water heat pump, no glycol. So how do we work with that? So first, Senko 2 has been around for, I think, about 15 years in the US and 25 in Japan. So they have a lot of experience, and we just leverage their experience for how to make those systems work well in cold climates. A lot of that is inspired from the solar thermal industry, which has been doing that as well. So you have heat tape and control. So maybe you should start the control in Senko 2. Whenever the temperature in the heat pump drops below a certain threshold, the heat pump will start whether the tank needs it or not, just to circulate water and make sure it doesn't get close to freezing. Heat tape to prevent pipe freezing, and even importantly, even though power outages, even they're not frequent, they do happen, and want to make sure that the heat pump still can survive power outages. And the way that is done is through a set of mechanical drain valves that don't need power and will basically drain, at least circulate the system, by opening up when the water drops below a certain threshold. It basically pulls warm water from inside the building, from the tank or whatever, or the plumbing, and basically brings warm water to prevent freezing. And then whenever that warm water comes, the valve's going to shut down or shut off, and until power is restored or the water gets cold again. But anyway, this is proven, works well when it's installed properly, and that's the key. It has to be installed properly. But what it is, it works well. We've had system happily working in Edmonton, Alberta for about a year and a half now, been through a winter in minus 40-degree temperatures, and hasn't had problems to date. So this is it works. It just means that it's important to have a quality installation to make sure it works correctly. The other concern that we hear sometimes is, what about operating duty cycle? How many hours does the Senko 2 operate, and does this have an impact on the warranty? So we have a lot of data. So one thing I haven't mentioned, but because we have a lot of sensors in the pod for control purposes, we can also use those sensors for reporting purposes. We have minute level data on every one of our system, temperature, flow, power, for every system that's connected. And we have MNV, level data collection on every system in the field. And what we are able to see is the median operating hour or operating time is about 6 hours on average annually, 6 hours per day. So it's about a quarter of the time. And when we were able to share this data with Eco2, they granted a 7-year warranty compared to 5 years for regular Senko 2 combis. So we do have a 7-year warranty on the Senko 2, 10-year on the tank, 10-year on the pod, and then the other devices like the air handler and whatnot is supplemental heat pump. That's per manufacturer warranty. All right, well, I think we're getting to the end. Obviously, it's easy for me to toot my own horn, but don't just take it from me. We're proud to have many organizations that have recognized the potential of our technology to change the game in terms of heat pump cost effectiveness and scalability. And this is my last slide. So in terms of takeaways, I think we're proud to have achieved our design objectives of high efficiency, low energy costs, low emissions, and grid friendliness. But we still have a lot of work to do. The challenge now and our goal is to scale the technology, which is primarily around cost reduction. So we're working on product evolutions that will reduce both equipment and installation costs. And we have a couple grants that are helping us doing that. DOE benefit, NYSERDA pending with our, I don't think Jason's on the call today, but with GTI Energy and Jason and his team, and we are looking forward to continuing to enhance the technology and continuing to deploy it. So that's what I have. I'd like to hear your questions and comments and get to the discussion.
Yeah, I have one, and then I'll pass it to other folks while they think of questions. What came to mind for me, I put it in the chat, is for those multifamily installs, is there a distinction between, and does it just need to have enough space for all the harvest components, or is there something specific about already having all the in-unit systems there?
Yeah, so we use the smaller tank typically for multifamily. It's the 80 gallon tank, which is 24 inches diameter. So it's still not a super skinny tank, but it's already, it fits in many closets. So far, we found space. I mean, obviously, I'm sure there will be cases where it'll be more challenging, but it's often a drop-in replacement for the existing gas water heater. And in multifamily, it's a little different. We have different air handlers, a lot of ceiling mount, soffit mounted air handlers. So we work with those. One thing we do in order to be able to get the single pass delivery is we have a custom coil in the air handler to be able to have single circuit high delta T across the coil. So that's something that we do in all the air handlers that we work with.
Okay. Okay, I'll pass it to John.
I'm not sure I answered your question, John, but if there's more, please expand.
Yeah, I was curious, I guess is it just a very large cost differential? Say you're doing like installing a cassette or two, but otherwise there wasn't pre-existing in-unit hot water or in-unit space heating. Is that a major cost differential? And so that's why you're suggesting that you only go after systems where it's all in unit already?
Yeah, I mean, if you have to retrofit a central into an in-unit system, I mean, it's all feasible, but there's a lot of plumbing and, a lot of maybe also, looking at space for the air handler, maybe adding a drop ceiling. So if it hasn't been done at construction, the cost is significant. So that's why we aiming to retrofit homes that were designed and built with in-unit systems, because from a cost perspective, it just makes more sense.
Okay. Yeah, I'll pass it to John.
Hi, thanks. Pierre, it's great to see how this has developed, and I really appreciate you including all of the data from your existing installations in this presentation. It's super useful. My question is, it seems to me that I understand why you are using the Sanco 2 because of its ability to make hot water for your thermal storage, but it also seems that particular product is a weakness for large scale expansion of this because has such a small capacity and because there's no cooling included. So I'm wondering if as products are developing, are you looking at other options for larger homes or for integration of cooling directly?
Yes, definitely.
And maybe that puts you on the spot with your primary heat pump supplier, but answer as you can.
Yes, no, I mean, first, many of our customers love the Sanco 2, right? They love the not having HFC refrigerants. They love the efficiency. So we're going to continue working with the product. It's a great product. But it is limited. You're right. It doesn't, the capacity is what it is. It's fairly low. So we do many systems with 2 Sanco 2s. When people don't want cooling, don't want a regular heat pump, they will basically get a heating only if they have radiant, if they have we see many systems with dual Sanco 2s, but it is still limited, and we are looking at going beyond that with regular air-to-water heat pumps, and that's part of the project that we're looking at with Jason and his team at GTI, and in other contexts. So we are looking at expanding our offering in terms of heat pumps. This is a starting point that works well, but it's not where we're not going to end or stop here.
All right, Chris.
Hey, Pierre. Yeah, I've been following, as you know, the Harvest Thermal story for quite some time. I was wondering if you can share just a little more detail about the cold weather applications that you've done. The performance slide that you shared with us, is that also representative of the Denver, Edmond, and other cold weather applications, or do you see significant differences in performance in colder ambience?
Yeah, it's a good question. We do see a temperature drop. I mean, the efficiency drops at colder ambient for sure. And you also have, yeah, I think outdoor efficiency drops. The efficiency is also impacted by the type of emitter that you have. And in some cases, one of the Edmonton site has a slant fin, so it's an emitter which is not super great at doing single pass delivery or high temperature delta. So the efficiency of that particular system is a little lower. I mean, it's still good, but it's not it's not as in the 3 range. So we do see efficiency varying. We don't have the cold climate deployments are a little newer, so we don't have a lot of performance data yet on those, and they weren't. That slide I showed, that was actually not last winter, but the previous winter, so they weren't included. I'm sure we'll see a broader range of efficiencies, and that's where we want to do more testing and more deployments to be able to measure this and make sure we understand what we get. But to be honest, we will see lower efficiencies as temperatures drop in near zero, or and first you have more defrost operation, and then you have sometimes you have backup, because if you have temperatures dropping below zero, then the capacity of the Sunco 2 reduces, and then we need to have backup heat. So the way we do backup, I haven't mentioned that, but we use a tankless electric water heater. Also, we do backup on the hydronic side, and the Sunco 2 continues to operate. So it's not like a switch from the heat pump to the electric resistance. It's just a variable capacity electric resistance supplement to the Sunco 2 to be able to meet the heating load. So it's also still very efficient, but it's you have more electric resistance, and the more electric resistance you have, the lower your COP is going to be.
Great, thanks.
Jason.
Hey, great overview. I think it might be interesting for this group to hear a little bit. One of your earlier slides, you had a comparison of the Harvest storage medium compared to PCM and conventional water tanks, and the fact that you don't have to have a buffer tank. Can you maybe share a little bit with this group about the role that tank stratification plays with your technology?
Yeah, thank you, Jason. So, I mean, it is key that we do stratified storage. Is highly stratified, right? And the reason for that is to be able to get the storage density that we have on this slide, right? It's because we are the storage capacity is obviously the product of volume and temperature delta across the discharge of the delivery system, and by being able to use 70-degree temperature delta or somewhere around there, and 120 gallon, that's how we can achieve this. If we were doing a mixed tank, we would have first. Well, it depends what temperature delta we'd have across the delivery system, but also using a mixed tank, we would not be able to have the efficiency and the speed of recharge that we get with the system. So we use we do external heat exchange. Sorry for going maybe too much in the weeds here, but we do external heat exchange to be able to keep stratification at all time and never mix the tank. So the whole system is designed to keep the tank stratified as much as possible. And just to give you a sense, I don't have a picture of it, but you may have the top third of the tank at, let's say, 145, 150 degrees, and then have a pretty sharp thermocline of just a couple of inches, and then have water at 80, 85, which is return temperature water, and then you have water at 40 or 50, which is domestic hot water, makeup water, and that's all stays stratified. And water that's returned to the heat pump is basically from the bottom of the tank. So you return the coldest water to the heat pump, and in single pass, bring it back up to 150 and put it at the top of the tank.
Any other questions from the group? I've got a few more I could throw out there.
Sorry, I missed a lot of the discussion while I was presenting in the chat. So please speak up if you have questions that you'd like answered.
Okay, we got one from Hugh.
Yeah, thanks. Yeah, it looks like an exciting technology. I guess, it looks like you're doing, I'm guessing, from a heating load point of view, you can meet the domestic hot water load, of course, and then you can meet, and probably you can meet about the same magnitude of space heating load. So it looks like on a daily basis, maybe half of your load is space heating and half of it's domestic hot water heating. Do you have any comments on that?
Yeah, it varies a lot by home, but what we actually see in single family homes is about 20% domestic hot water and 80% space heating. And in multifamily home, it's actually either more balanced or sometimes higher domestic hot water. But in single family home, space heating typically dominates as the majority of the heat output. And water heating load is going to be, depends on the home again, but it might be somewhere around 30 to 40,000 BTUs a day. The Sanko 2 capacity has a capacity of about 300,000 BTUs. So, if the Sanko 2 were running 24 hours a day, which is not the goal, which doesn't happen very often, but the maximum capacity is 300,000, and domestic hot water is only about 10% of that.
Yeah. So okay, so it's your high delta T distribution that allows you to meet more space heating load than say like Sandon. So I remember, I haven't looked recently, but they used to say that you only could meet a third of the load should be space heating. But because you're doing high delta T on space heating, you've been able to drive that higher.
Yeah, we use the storage tank as a big buffer tank if you want. So while think of the Sanko 2 as a trickle charger in EV terms, it provides direct heat, only a small portion of the direct heat. Most of the heat comes from the thermal battery. So you can meet about up to 4 tons of heating load from the thermal battery, obviously only for a couple of hours. And that's why we need that auxiliary heat pump if you have more than, if you have a 3 or 4 ton load. You're going to need to, once the storage runs out, you're going to need to run the other heat pump while the Sanko 2 recharges storage. But the instantaneous capacity of the system is around 4 tons, maximum 4 tons. And the first 2 tons roughly is going to be provided by the hydronic system, and beyond the 2 tons, anything above 2 tons can be provided by the supplemental heat pump.
Gotcha. So in cold climates, you really need the other heat pump to kind of meet the loads, basically.
Or you need a very small, efficient house, like a passive house, or very efficient house with 2 Sanko 2s. That could work too, but in most cases, yes, you'll need a supplemental heat pump.
Okay, thanks.
Take one more question from Bill.
Thanks, and I just have a quick question. Looking for buildings that are good criteria in multifamily, if we have a central boiler, it's pretty much a non-starter.
Unless you want to, you are able to repipe to being in unit. But yeah, if it's without repiping, the system is not designed to do a central plant. It's designed to do in unit. So yes, it has to be either existing or retrofit.
Or move to. Okay, thank you. Just verifying that.
Okay, great. I don't want to push us too past time. So thank you, Pierre. I appreciate it. Might send you some questions via email later.
Sure. Thank you all.
I'll jump back to presenting. So first off, I wanted to announce that HPWH is planning an air to water heat pump manufacturer roundtable. And I don't believe we have anybody signed up yet, but Vidisha can correct me if I'm wrong. But we're sending out a call for manufacturer representatives. The idea is, this would be a 90-minute session, but, with short presentations on new and upcoming products from the manufacturers, then a lot of open discussion questions. And the key thing with this is this will be advertised independently of the Hydronic Heat Working Group. So you'll get a little bit more reach if you were hoping to show off some new products that you have out on the market. Let me know if you have questions about that, or fire an email to Vidisha and I, and we can get you in the pipeline to get signed up. I do this call every meeting, but if anybody has new reports or presentations, or wants to give a brief update on any exciting activities, projects, or programs, feel free to do that now. I am also interested if, this came up on a project recently. If anybody has short best practices guides of the kind that, one could give an installer who has some heat pump experience and some hydronics experience, but isn't an air to water expert on how to go about installing air to water systems successfully with existing hydronics. Is there anybody who has a good guide in their back pocket? I know we kind of clicked around Vermont's website because you have the qualified products list, but we couldn't find anything that was just a nice short piece of information.
John, sorry, can you clarify, are you looking for sales type literature, or are you looking for installer like tips and tricks type literature?
Yeah, it's
Like
kind of an
looking
installer tips and tricks type literature. Like, I've seen articles on best practices. I've seen some, 60-page best practice guides, but I haven't seen 2 to 4 pager type things that lay out the key pitfalls and tips and tricks.
I agree, it would be a great resource.
I'm sort of asking because I'm wondering if this group could hold a session, working session where we discuss amongst ourselves and identify those things and then try to build up our own guide. So I guess stay tuned for that, or let me know if you have anything that you've seen that'd be that'd fit the bill. Anybody have any updates they want to give before I move along? All right, final housekeeping slide. I am interested in convening inside this group a panel on program design and program results. I know that air to water heat pumps are incentivized in some programs. I've received some emails to that effect. So if there is anyone from an REO, a utility, or who is a program administrator that is interested in signing up to be on a probably 4-person panel inside of this working group, it would be really great to have your attendance. So let me know, send me an email, and we can talk more about it. Other than that, always open to get presentation panel and working session ideas. And our next meeting is on May 16th. Any closing thoughts or questions from folks in the group? All right, well, I pushed us so fast that we got done slightly ahead of time. Thank you everyone for joining. And I'll stick around until the end of the meeting, but I think that closes it.